This video is for section 2.3, equations of value for multiple deposits. So we have multiple contributions labeled C0, CT1, all the way up to C sub Tn. So the subscripts are the times at which the contributions or deposits are made. If under an accumulation function, the balance of these contributions at time capital T is B, then we list, we place the balance here. If we would draw the balance, then we would put a negative sign in front of it from the standpoint of the account. So as the account receives the contributions are positive, if we would draw contributions from the account, we would use a negative value. To write the equation of value, we first take the net present value of the cash flow or the contributions at time 0. So the net present value of the contributions, we take the present value of each individual contribution using the accumulation function. And that's the net present value of the contributions. So that would be the value at time 0. If we then bring that forward with the accumulation function all the way to time t, that should be the balance. So we bring all this forward using our accumulation function evaluated at time t, and that should be the balance of the account. So that would be the equation of value. If we now divided both sides by a of t, then the equation of value at time 0, we're discounting both of these sides of the equation all the way back to time 0, is given by this expression. If you wanted to value these contributions and write down the equation of value at a different time, rather than at time t after the contributions, we could value the whole set of contributions at time tau sometime during the time we're making the contributions. So in that case, we would take the net present value of all the contributions, and we would bring that net present value forward to time tau. And then we would bring the balance at time capital T back to time tau. And we see that we've done that here. Of course, we have to really bring the balance back to time 0 and then back to time tau. And we see that expressed on the right side of the equation. And so this is just modifying this equation of value at time 0 by bringing each term in that equation forward to time tau by multiplying by a of tau. If we want to value these multiple deposits at maturity at time t, then of course that's what we did in the very beginning at the start. And so we can summarize that equation of value right here. Okay, so let's apply this to an example involving a loan. So we're going to borrow $10,000. The loan interest rate is 8%. We're going to make a $5,000 payment at the end of year 1 on this loan, a $3,000 payment at the end of year 2, and we want to know what is the payment amount P at the end of year 3 that will pay off the loan. Notice on the timeline, from the standpoint of the borrower received $10,000, so what the borrower receives will make, by convention, positive, and then what the borrower pays, by convention, we will make that negative, and that's why the payments to pay off the loan are all negative. So the principle involving loans is that the accumulated value of the payments should equal to the accumulated value of the loan. Alternatively, we could say at time 0, in the margin here, at time 0, the present value of the loan must equal to the present value of the payments. So this is how we value alone, and what I circled to the left would be the time 0 equation of value. Now, if we want to write down the equation of value at time 3, as is asked for here, then we need to take the accumulated value of the loan. So that would be 10,000. This is going to be using 8% compound interest. So we'll accumulate that to time 3. So that is a loan accumulated to time 3. And that has to be equal to the payments accumulated to time 3. So the $5,000 has to be accumulated for 2 years. That's a loan interest rate. The $3,000 has to be accumulated for a year. And of course, the final payment P is at year 3, so it's not accumulated at all. So this is our equation of value at time 3. We can solve this for P very easily doing the arithmetic. We get P is equal to 3,525.12, and you should do the arithmetic and verify that. If we wanted to write down the alternative equation of value, that would be the equation of value at time t equal to 0. So now we're going to write down the present value of the loan is equal to the net present value of the payments. So we have at time 0, the loan is worth $10,000. We receive it. The net present value of the payments using the loan interest rate, $5,000, is discounted back 1 year. $3,000 is discounted back 2 years. And the final payment P occurs at time 3, so we have to discount it back 3 years to time 0, and that's the net present value of the payments. They have to be equal to the net present value of the loan. If we look at example 2.3.6, we deposit $5,000, $3,000 year 1, $2,000 at year 2. And the question is, what annual effective interest rate is necessary to have a balance of $11,000 at the end of year 3? So I've placed the cash flows on this timeline already. You see the balance of $11,000 at time 3 I've circled. So below that it says, what is the equation of value at time t equal to 3? Well, at time t equal to 3 we have to accumulate all of these contributions, and that has to be the balance at time 3. So 5,000, we need to accumulate it at 1 plus I cubed. We don't know what I is. That's our unknown. $3,000, we use the compound interest accumulation function and evaluate it at time 2. And $2,000 we accumulate for 1 year, and that has to be equal to the balance at time 3, which is $11,000. So that's my equation of value at time 3. Now, the left-hand side I'm going to put in function notation. I'll call it P of I. If we evaluate P at 0.04, so when the interest rate is 4%, we will get a certain value, and you can do that. You will get on the left side $10,949.12, which is not $11,000, but it's pretty close. If you evaluate it at 5% interest, 0.05, you'll get $11,195.62. Therefore, the solution to this equation for I must be somewhere between 4% and 5%. So we could just sort of try to guess at I. We could guess at 4.5% and see if that accumulated value is larger or less than 11,000, and we could continue sort of in a bisection method. But there are several ways we can go about this mathematically. One method we could do is use our cash flow worksheet. And so we're going to use our BA2 Plus calculator in our cash flow worksheet in just a minute. But let's look at the questions concerning this problem. First of all, this is a polynomial equation in 1 plus I. We have powers of 1 plus I on the left side. It's a cubic equation. So we can ask the question, is there a unique solution? And it turns out that there is a unique solution to this. And the answer to that question being yes, we're going to have to study some theory from algebra, just from the theory of equations, as to why this would have a unique solution. Because potentially, since it's a cubic, we could have three solutions to a cubic equation. A cubic polynomial can cross the axis 3 different times. So if we have a unique solution, then that means the cubic polynomial in the equation only crosses the axis a single time. So then that brings us to the question, how do we solve polynomial equations? And here we're going to look at root finding techniques. One of which is Newton's method. So we're going to explore Newton's method briefly also. Now, to use our technology, let's go back to our calculators. And we can use our cash flow worksheet. And remember to enter into your cash flow worksheet. You want to hit the cash flow button on the second row and hit second clear to clear the worksheet, and then begin entering your cash flows. So the first cash flow is 5,000. Looking at our timeline, at time 1, our second cash flow is going to be 3,000. Another unit of time down the timeline, our cash flow is 2,000. And then at time 3, we're going to enter the balance as, or the right-hand side of the equation and the equation of value at time 3 as a negative. So the balance will be at the opposite sign of the contribution. So here we're assuming that we're liquidating the fund or the account at that time, and so therefore that's a withdrawal. We're withdrawing the balance. Once you've entered these, if you then hit IRR and compute, we do get a value, and that value is about 4.20965, or about 4.21%. So the cash flow worksheet allows us to find a solution. It's important to know if this solution is unique so that we know we found the solution. If the solution is not unique, then we just found one of possibly several solutions. Okay, so let's review Newton's method. So in order to review Newton's method, let's remember that Newton's method is used for solving the equation f of x equal to 0, where f of x is some function. In our case, f of x is going to be a polynomial, and we're going to use Newton's method to find the roots of the polynomial by solving the polynomial equal to 0. Here's the Newton's method formula. It's an iterative formula. And first, let's define our polynomial. We're going to let 1 plus I be equal to x in our equation of value. So I'm looking up at my equation of value at time 3. I have p of x is 5,000 x cubed plus 3,000 x squared plus 2,000 x, and I'm going to bring my 11,000 to the left side of the equation, and I get minus 11,000 equal to 0. So that's my polynomial equation. And looking up at Newton's method, I not only need my polynomial, I'm going to need my the derivative of my polynomial in the denominator. So I'm going to take the derivative, bring the power down and raise it to the 1 less power, and I'm going to get 15,000x squared plus 6,000x plus 2,000. And I'm going to use that derivative in Newton's method. Now with Newton's method we have an initial guess, and so x is 1 plus I, so if I think the interest rate is somewhere close to 10%, then my first guess is going to be x naught equal to 1.1, or 1 plus the interest rate, because that's my 1 plus I is the variable. So that's my initial guess. Newton's method will then give me the next guess through this recursion function, the recursion relation. So x1 is equal to x0 minus p x0 over p prime x0, according to Newton's method. So it's equal to 1.1 minus p, the polynomial evaluated at 1.1, over the derivative evaluated at 1.1. And I have an expression for the polynomial and its derivative above, and you can do those calculations on your calculator, and you'll get 1.1 minus 1485, that's the polynomial evaluated at 1.1, divided by 26,750, that's the derivative evaluated at 1.1. And that gives me a second value, x1, of 1.044486. I then want to store this in my calculator in the first position. So you can hit your store key and your 1 key to store that answer. We're going to recall that because this Newton's method says I then need to calculate x1 minus p of x1 divided by p prime of x1 to get my next guess. So I'm going to hit the recall button. It's going to recall that value, and I'm going to subtract the polynomial evaluated at that value over the derivative evaluated at that value. So you would have to actually do these two calculations, the polynomial evaluated at 1.044486, and you'd have to calculate the derivative evaluated at that value. If you do those calculations, of course, you have 1.044, and if I round to the 4th decimal place, I have all the values in my calculator, but writing them down, I'll just round to the 4th decimal place. The polynomial evaluated at that interest rate is 57.5851. And the derivative evaluated at that interest rate is 24,631.70. So then there's a lot of arithmetic to do there that I did beforehand that you need to verify so that you can do that on your calculator. And at least to 4 decimal places, I come up with 1.0421. And you see already I'm close to what my cash flow worksheet gave me to 4 decimal places, just after a couple of iterations of Newton's method. So the solution is approximately I equal to 4.21%. I do want to make a couple of comments here before we go to the next page. I believe when you do this calculation up here that you're going to get 4.20765. So I think that is a typographical error in the answer I circled. With enter cash flows IRR compute underneath that. If you would change that 9 to a 7, I believe that's what you will get. But rounded to 2 decimal places, or 2 decimal places, it is going to be 4.21%. The other thing I'll mention is we did answer that question about this problem having unique solution. We said it was yes, and this will be a topic for the next section. How was I able to answer that question yes? So We will explore that later. And let's go to the next page. So this is an unknown interest rate type of problem with the equation of value. You see, they can be really quite complicated, and we have to utilize technology. We're normally solving a polynomial equation in financial math. Okay, the next page, the other possibility is unknown time. And here we're going to borrow $1,000 in example 2.37. We're going to make two equal payments of $525 at the end of year T and at the end of year 2T, and that's already on the number line. You can see here the two payments at time T and 2T. If I is equal to 10%, we want to know what is the value of T. Okay, so the equation of value at time 0, we're going to use the loan principle that the present value of the payments have to be equal to the present value of the loan. So the loan amount is going to go on the left side, and the present value of 525, well, using compound interest, we can just discount a v and raise it to the t power, which, by the way, if you remember, is 1 over 1 plus I to the t. So we're just discounting back 525 to time 0, and then the second $525 payment has to be multiplied by v to the 2t because we're discounting it back 2t years to time 0. So we have the present value of the loan is equal to the present value of the two payments. Notice that we can write this as a quadratic equation. We can, starting with the term on the far right, we have 525 v to the t squared. Whoops. I don't want to include that parentheses here. 525 times v to the t squared. So that would be 525 v to the 2t. Now 525 v to the t. And then I subtract the 1,000 to the right side, and that gives me a quadratic equation in the variable x equal v to the t. So since I have a quadratic equation, I can utilize the quadratic formula. So you should pause here and see if you can solve that quadratic equation for v of t. Okay, if you solve the quadratic equation, I've written the quadratic formula here, and you can see I've substituted in the coefficients, and if you do the arithmetic, you only get one positive answer that makes sense in our context. You get a negative answer, negative 1.708, and that root does not make sense in the context of our problem. So what do we have? We have v of t, v to the t is equal to 0.96791. And what is v? v is 1 over 1.1. So we have an exponential equation, the unknown is a power, and you can use the natural log to solve for time, and when you do, you'll get time is equal to 3.42 years. So that's working it out using the quadratic formula. You can also use your cash flow worksheet. It's possibly a little quicker. If you would put your cash flows in, then let's see, at time 0 you have a cash flow of 1,000. So from the standpoint of maybe viewing, you could put negative 1,000. We're going to go ahead and put positive 1,000 for the amount borrowed since we received that. Cash flow at time 1, that's going to be our payment, so we'll associate a negative sign with that payment, negative 525. Cash flow at time 2, also negative 525, where when I say time 2, we have equal increments of time here between the cash flows. So the unit of time, a unit of time is t years in this case. So there are t years that have elapsed between each of these cash flows. We want to keep that in mind. Now, when we hit the IRR and compute, with respect to these cash flows, we're going to get the 3.33153%. And so since a unit of time is t years, that means that 1.1 to the t power is going to be equal to my 1 plus the IRR that I just computed. I have a unit of time of t years between these cash flows. My annual effective interest rate is 10%. So I can solve this equation for time. Again, it's an exponential equation. As a matter of fact, it's the same exponential equation as before. If I just take the reciprocal of the equation that I had when I used v of t, and again I get t equal to 3.42 years. So using the calculator, we can, as long as we have equal increments of time between cash flows, we can use the cash flow worksheet to solve for an unknown time problem. As a final example of unknown time, we're going to consider a sequence of cash flows in cash flows at times t1, t2, all the way through tn, and I've already placed them on the number line below. And the problem is to find such a time t, capital T, such that a single contribution equal to the sum of all those cash flows, and a single contribution we're going to call capital C. So a single contribution equal to the sum of all those individual cash flows at this unknown time, capital T, has the same present value as the net present value of all of those cash flows. So we just set up an equation of value. So we take the present value of this single contribution, capital C at time t, that's one side of our equation of value, and the other side is just the net present value of all the individual cash flows. So I'll just write that net present value in summation notation. So we can solve this exactly. It's just a exponential equation. So if I divide both sides by c, let's see, I'm just multiplying this sum by 1 over c. I'm going to go ahead and distribute that 1 over c to each term in the sum using distributive property of multiplication. So it looks like this. And then I need to take the natural log of both sides and bring the power down. So I'll do that. Okay, and then divide by the natural log of v. So I can solve that exactly, it's no problem. There is a way to estimate that time, and we're going to see that below. Before I do, notice how we've weighted the discount function at time t sub k. We've weighted, in the numerator, we've weighted the discount function by these weights. The cash flow that occurs at time t sub k divided by the total cash flow. And so we're going to utilize this type of weighting system below in the method of equated time. But let me make this weighting system clear with this little example. Suppose I have cash flows of 5 at time 1, 10 at time 2, and 5 at time 3. My total cash flows would be 20, right? And so my weights would be the cash flow at the time divided by the total cash flow. So my weight at time 1 would be 5 over 20. the weight at time 2 would be 10 over 20, and the weight at time 3 would be 5 over 20. Notice my weights add to 20 over 20 or 1. So weighted averages, the weights must always add to 1. So this is the type of weighting system that's used in the numerator above, but it's also going to be used in the method of equated time given in the last paragraph here. So the method of equated time, the approximation to the time where this single lump sum cash flow occurs, is denoted by T bar. And so T bar is just going to be this weighted average, and you're taking a weighted average of the times at which the cash flow occur, where the weights are the cash flow over the total cash flow at that time. Okay, so let's illustrate this in an SOA question. So in this SOA question, it says a payment of 400 at time 2 plus a payment of X at time 5 is equivalent to a single payment of 400 plus X at time 3.125 using the method of equated time. The two payments are equivalent to 400 plus X at time t equal to K using the exact method and an annual effective rate of 10%. We want to find K. So here we're given two statements with information, one using the method of equated time, the other using the exact method, and we want to apply both of these formulas to find the unknown that's asked for. So let's draw a picture first, and let's use the method of equated time first. So the method of equated time, the picture is going to be like this. At time 2 we have a payment of 400. At time 5 we have payment of X, so we don't know, but we know that this is equivalent to, or has the same present value as a lump sum payment of 400 plus X at 3.125 using the method of equated time. So the time at this arrow here is not T, but it is, of course, T bar. So let's write down the equation for T bar. Then. So we have T bar is equal to, so the sum of my cash flows is 400 plus X. So the weight at time 2 is going to be 400 over 400 plus X. That's the weight at time 2. The weight at time 5, which is where the cash flow X occurs, is going to be X over 400 plus X. And so that will be my T bar, which I'm given is 3.125. So I have one unknown, X, and you have to solve this equation for X. And when you do, and you probably need to pause and do this, you'll get, if you pause, you'll get X equal to 240. So you should make sure you can do that algebra. And by the way, the algebra involved is you multiply both sides by 400 plus X, right? And then you just isolate X on one side of the equation. Now the next sentence contains the unknowns. It says the two payments are equivalent to 400 plus X at time t equal K using the exact method. Okay, so let's use the exact method. Using the exact method, I have 400 discounted back 2 years using 10% interest, compound interest, and the $240 payment, the X, which I just found, discounted back 5 years. And that is equivalent to 400 plus X, which is $640, discounted back K years, because it says 400 plus X at time t equal to K using the exact method. So we'd multiply this by 1.1 to the minus K. Well, this just gives us an exponential equation for k. Once again, we can use the natural log and we can solve that exponential equation. And again, you should do it, and you need to verify that k is 3.027. So this is a typical SOA question using the exact method and the method of equated time in the same problem, just to see if you know both of those methods. Of course, you have to be able to write down the equations of value, and from those equations of value find an unknown. Okay, so let me review quickly what we've done. It's been a rather long pencast. We started back defining the equation of value. We can have the equation of value at different times, at time 0, or the equation of value at the very end or maturity at time capital T, or any time in between. We normally use the equation of value either at time 0 or at the end of the time when we're paying off a loan or calculating the balance or liquidating the account. Those are the two most common times to write down an equation of value, but you have to pay attention to the time that it tells you to write down the equation of value. Okay, and also notice that even though the general equations of value are written down with respect to any accumulation function, that in our examples we used compound interest. So here we're starting to use compound interest more and more. We saw that when we have an unknown interest rate, this led to a polynomial equation. In particular, in our example, it led to a cubic equation. And we see that we need to know when a polynomial equation has a unique solution and when it has multiple solutions. So we're going to study that in the next section. We see that we need to know root finding techniques, and we can use our cash flow worksheet in our calculator to find the roots of these equations of value using our IRR computational functionality of the calculator. And we also have seen an example using Newton's method, an iterative method, for approximating the roots of these polynomial equations that come from the equation of value at time 0. So we're probably not going to utilize Newton's method a lot since we have the technology, but this is something for you to be familiar with. And then we have the case of unknown time that's involved in an equation of value. And these unknown time problems normally result in an exponential equation where we have to use a logarithm to solve for time. And then there is a special case where we're interested in knowing a single lump sum cash flow at a particular time, where the single lump sum cash flow is the sum of all the individual cash flows that has the same present value as the net present value of the cash flows. And we can find an exact solution, and we can approximate it by taking a weighted average of the contribution times, and this is called the method of equated time. So this is a quick summary, or I just went through a quick summary of a rather lengthy section. This is a good section to spend some time on and to master, and it's utilized quite heavily from this point forward in the course.